transmitted to different progeny. So the experiment is you inject and that fish grows up to be mosaic. That means if you outcross it, different F1 progeny are going to have, as I say, different inserts. So the first thing we had to do was to show if these inserts could be mutagenic and make embryonic lethal mutations. That was our goal. So at first we did a pilot screen. We took fish with individual inserts, outcrossed them, inbred the insert, and asked, do you see a phenotype in the developing embryo? And these were the dark days of our lives, believe me, because it turned out, first we started out, and the question is, what frequency would you expect? How many genes are there in the genome that have this property? If you mutate them, you'll see a visible defect in that first 5 days of life. How many genes should there be? How big is the genome? How many genes are there? How many numbers do you have to, how many inserts are you going to have to look at? And it turned out that the frequency was about 1 in 80. About 1 in 80 inserts caused the mutation that resulted in visible phenotype. This is very low, and we were extremely depressed. In mice, it's about 1 in 15 to 20 inserts. So it was quite discouraging. And what made it possible to do the project was that we saw that if the virus had very high titer, sometimes F1 fish that resulted had multiple inserts in them. And the only way you were going to ever be able to do this project without taking over the entire building, cancer center building, and this is how gender equity studies came to correlate with scientific work, space. Everybody knows space is hard to come by. So anyway, long story, I'll skip the gender equity part, but say that we finally figured out we could reduce the amount of space needed by having multiple inserts in each F1 fish, and if we could select those fish and use them as the starting population, then all the work you did was going to be reduced hugely. So that was the actual experiment, and here was the actual protocol of the experiment. Inject close to 1 million embryos in the F3 generation. I should say for 2 years to get that project done. Well, first of all, let me thank you and Jim for the money. And then I should say to actually do it, we had a fantastic team. It turns out a lot of people go to college to major in water and fish work. And then they find it's hard to get jobs that they really want in wildlife and so forth. They were thrilled to come to our lab and be the people who did this work and much of the technical work. And they were wonderful. And we had 15 technicians for 2 years who really plowed through these enormous numbers of fish. So it was a great experience. So at the end of the day, we think we made about 400,000 inserts of the germline of those 32,000 pounder fish. We only screened, because of the way the protocol works, about 45,000 inserts in the F3 generation. And as I told you, only about 1 in 80 insert is going to give a mutation. So what did we actually get? How many mutants did we get? How many different genes? And what fraction of all the genes you could hit is this? In other words, how many embryonic leads, how many genes are there that if you mutate them one at a time, give you a visible embryonic phenotype? And here's the answer that we got. We got a total of about 500 mutants, and we think they represent close to 400 different loci. Of those, the junction fragments for the mutagenic insert have been cloned from most of them, and they represent this many different loci. And the number of genes that have been identified is this. So a large fraction of the genes that have been cloned from this screen already. And what's interesting about them is, first of all, these genes have human homologs. They're not some peculiar kind of fish gene unique to the fish. They are, with the exception of 2 genes, all of them have we found the human homolog. 20% of the genes, roughly, are novel, depending how you define the word novel, but biochemical function is unknown or unclear. And one of the most amazing things about it is essentially all of these genes, all the molecular work was done by one person. And his name is Adam Amsterdam, and he came to my lab as a graduate student and stayed on as a postdoc, and he's still in my lab. And he is the most amazing person and very hardworking. And it really was an incredible accomplishment. And I say this project is every bit as much his work as it is mine. The question is, when you do a screen, as you know, the critical thing is what fraction of all the genes do you get? And of course, everybody would like to get to saturation and get all the genes. That didn't happen. What fraction did we get? We think that the loci that represented molecularly in our collection is about 25% of the genes that can be found by this approach. That is, genes that you knock it out one at a time makes a visible phenotype in an embryo. The reasons for arguing that are the following. There are about 79 or 80 different ribosomal proteins, and they're not duplicated in fish as far as we can tell, so that means about 80 genes, and we have mutations in 27 different ribosomal protein genes out of the 80. There are 20 tRNA synthetase genes. We have mutations in 5 of them. There are 100, at the time of this slide was made, and I can't remember when it was made exactly, we had mutations in a quarter of the genes that had been identified in the chemical screens and then positionally cloned. And no matter how many genes have gotten cloned from by other means, by other people, we always end up having a quarter of them in our collection, have insertional alleles a quarter of them. So these things all argue, in fact, that we have 25% of the embryonic lethals. So that means the number of embryonic lethals is really small, only about 1,400. And this is something that I totally find fascinating. Nobody else does but me, so I don't talk about it much anymore. I tried it out on a mock audience and didn't meet with great warmth, so I will spare you. I took those slides out. But basically, I find this fascinating for the reason that the number of essential genes is really similar, very similar, I think, in most organisms that have been looked at. And the number is very small. And basically, it looks as if, in, say, yeast, there's about 1,000 genes that are essential, genetically essential, in that if you knock it out, you're dead. And then there's several hundred more for making an embryo and a few thousand more for making an adult animal. And those numbers look similar, whether you look at flies, worms, fish. And it leads me to think that it's a meaningful result. We also did an analysis, Adam Amsterdam did an analysis asking, are the genes that are essential in the fish the same as the genes that are essential in the fly? And the answer is hugely so. That is to say, the trait of being an essential gene as opposed to being a redundant gene is conserved through evolution, as if there was some purpose to that.